Okay, so now let's see how we can use other forms of energy. We keep only using kinetic and potential. So we learned the formula for springs for elastic potential energy. So yeah, just as a reminder, right, the elastic potential energy or spring potential energy is half kx squared. And just to be precise, it's delta x. It's the change. This is the displacement from equilibrium, right? Whenever you write some formula, make sure you label the symbols, and K is called the spring constant. Okay, and yeah, so those are the energy it stores. So you see, the more you displace from the equilibrium, whether you squeeze, this is squared, so it doesn't matter whether the displacement is positive or negative. So whether you stretch or compress the spring, for most springs, if you compress it at the same amount as you stretch it, it stores the same amount of energy, right? So if you if you pull it and pull it by 2 centimeters, release something, compress it by 2 centimeters, release something, usually it will push it with the same force, or pull it with the same force. And so you see the energy sort of, it's squared, it doesn't care whether you push or pull. That's usually, or at least to first order, that's most springs behave. Of course, I'm sure you can come up with some springs that do not do that. But yeah, we'll look with simple case first. That's the beauty of physics. You look at simple case, complicated, at least as a beginner, you don't have to worry about it. All right, good. So I keep saying sometimes you can buy you can buy a spring, and then it'll usually have a label and say what's the spring constant, right? That's how much it changed. If you look at the force approach, it basically tells you if you apply a certain force, how much it will change, right? So in some sense, if I just look at the magnitude, if you apply some amount of force and it changes a lot. So if you apply some force to a spring and it changes a lot, that means it has a small spring constant. If it changes only a little bit, it has a large spring constant. So in some sense, the spring constant is a measure of the stiffness of the spring. Okay. So yeah, if it changes a lot, that means it's not very stiff. It's very flexible. If you apply some force, like let's say 10 newtons, and then it just changes by a tiny bit, like 0.1 meters, or even worse, right? 0.01 meters or 1 centimeters, then 10 divided by 0.01, everything in SI units, will give you a large number. That means it's very stiff. You apply 10 newtons of force, it barely changes. Okay, so that's what the spring constant is. But how do we measure it? Well, I've described one way of measuring, but let's try another way, see if we can use the energy approach. Let's drop a mass over here. Let's say we'll drop a 1 kilogram mass, okay, pretty massive, at some height. Okay, so let's say, again, drop it from our favorite height, 30 meters, and drop it onto a spring. And so it'll hit the spring like this, right, and hit drop, and it will compress it a little bit, right? It'll compress it a little bit. And we'll go about and measure how much it compressed. So the maximum it compressed, let's say it compressed just 0.5 meters, right? Around 50 centimeters. It's a long spring. All right, we'll just make up some numbers to work with. All right, can I determine the spring constant? This is one way to measure the spring constant. Just take a mass and drop it. All right. Well, you can do this. You can do this with the force approach. Use F equals to K minus K delta X. In this case, delta Y, but I can make the vertical my x-axis. It's one-dimensional. And you can draw a free body diagram over here. You see a pushing force upwards. You can see the weights. You can see normal force. All right, you can do all that, but the energy approach is going to be easy, right? So let's see how that works. You start off over here. What are the energy? Let's do an energy analysis, right? It's almost like a free body diagram step. You analyze all the energy here, but instead of looking at forces, you look at energy. So I drop it from rest, so kinetic energy. So this is my point 1, step 1, step 2, step 3, right? So it's going to be 0. The potential energy, the gravitational potential energy, depends on where I set my height, right? MGH and H1. So depends on where I set my height. Where do I want my 0 to be? Well, if I set my 0 here, I don't really know how long the spring is. I know it will compress by half a meter, but what's left? I did not say it's originally 1 meter. If it's 1 meter, then there's 0.5. But if it's originally 2 meters, then there's still 1.5 meters here or whatever, right? So I don't know. So if I set the height here, I have no hope of knowing what the height, I don't know what's the original length of the spring. So let's set the height at the relax sort of, this is the equilibrium position of the spring, where I should say the relaxed position. So this is the relaxed position. And I'll set this to the height close to 0, right? So in that case, this is easy. This is mg30. Okay, and over here, well, I really want to find the spring. Here, the spring is not really compressed. So there's no spring elastic potential energy stored, right? It's just relaxed, so there's no energy. Here, so this is the point where I want to compare. So here, what is my kinetic energy? Well, here, when it's maximally compressed, so I say the maximum compression is 0.5, let's say, right? The maximum compressed, you can see the maximum compressed is when this is 0, the speed is 0, right? Because if the speed is still going, then it'll compress it more, right? So the speed has to be 0, so K3 has to be 0. What's the gravitational potential energy? So what's U3? Well, mgh, yes, but what h, right? The m is still, I'm talking about the energy of this guy. So the height is going to be minus 0.5. So it's mg minus 0.5. Okay, we can plug in the m and g later on. Okay, so now notice what's going on. If I just equate 0.1 and 0.3, the kinetic energy here is 0 because I'm dropping it at rest. I drop at rest. So nothing changed over there, but what is my change in potential energy? Well, it went from mg30 to mg minus 0.5 or minus mg 0.5. So did my potential energy, did my gravitational potential energy increase or decrease? It went from 30 times mg to 0.5 times mg or minus 0.5 mg, so clearly decrease. So where did the energy go? Well, the answer is there, right? It went into the energy stored in the spring. Okay, so there again, you can view it in a couple of different ways. You can view it in terms of all the change in potential energy. Any decrease would become any increase in the spring potential energy. So I don't know there is a symbol for it, so I'm just going to call it E spring, the energy in the spring. Okay, yeah, so it will have change in E spring, but if this guy increased, this guy decreased, right? So so we put a minus sign here. So this increase, this decrease. So this is one way of looking at it. The other way is just add up the total energy. In this case, it's probably less. In sort of kinematics problems, it's useful to match your change in K to the change in U, one gain, one loss. Here is also possible, the loss in potential energy, because it went from a high height to a low height, it creates a gain in spring. So you can use this relationship. Again, I'm training you to use that in terms of heat later on, because it's more convenient to do in 3B later on. But in this scenario, we don't use this that often, like kinetic and potential. So maybe it's easier if we just match up the E1 total to E3 total. Okay, so let's see if we cannot do this. K1 plus U1, that's the total energy over here. You can put the spring's energy, but it's at a relaxed position. So remember, this is displacement from relaxed position, from relaxed or equilibrium, right? So that is 0 because there's no displacement from the relaxed position. So you could put it there if you want to be complete, the E spring. I'll just do ES because I'm getting lazy. But that's going to be 0. The kinetic is going to be 0. You have mg30 over here equals to K3 plus U3 plus E spring 3 at 0.3. Okay, so 0. Okay, here the kinetic energy is 0 because energy is conserved. So whatever total energy you have, my system is including a spring now. So everything, and we need to do a big closed system, right? So all the energy has to in the system has to be taken into account. So yeah, so you add these up, and here you add these up, plus mg minus half a meter. I'll use half so I can sort of do some mental math later on. Plus, yeah, actually, you know what? That's not a good practice because, again, for whoever's grading my work, you want them to be able to match things up. So that's a slightly better practice. And E spring is half K delta X. So what's the change in equilibrium? So it went down by 0.5. So delta X is minus 0.5 from the relaxed position squared. It's in meters, okay? So that's done. You see the minus sign isn't too important over there, but just for consistency, again, for whoever's checking my work, they can tell. All right, so what is my goal? My goal is to find K. Before we even sort of jump into it, it's good to take a take a different color pen and check off things you know, so you know where you're going with it. Do I know M? Yes, I know M. Do I know G? Yes, I know G. So I know for sure I can solve for K. All right. Should I do it, or can I leave it to you? Yeah, let me do it. Yeah, but yes, at this point, remember the physics is done. All is math. The rest is algebra. Okay. So sometimes it's helpful when you study physics, learn at what point you're done with the physics, and the rest is just math. Right. I know it doesn't, for a lot of you, it doesn't make it any easier. Math is still another issue to resolve, but still, now you know where your difficulty is. Do you not understand the math problem, or do you not understand the physics part? If you don't understand the physics part, figure that out. If you don't understand the math part, know that you at least be comfortable that, all right, my physics is fine, and now I just need to practice my math and get my algebra in order. You know, so it gives you a focus of what to study and what to prepare, and you don't have to feel bad on, oh, I don't know, I'm really bad at this subject. You know exactly what you're bad at, and that way you can improve. So by identifying exactly where your weakness is, etc. Okay, yeah, so how would I do this? So let's see. So first of all, there's a lot of zeros. Let me simplify that a little bit. And maybe, yeah, I'll just simplify the zeros first because they're annoying. So it clouds up my judgment. So we'll put it here, minus, now I can do sort of the math part. So because you just distinguish, that's the physics, that's the math, plus 1/2 K 0.5. So that's 1/4. So K times 1/4. 0.5 is 1/2, but squared. So it's 1/4 for 1/4. Okay, I want to find K. So let's isolate this whole term. So I have essentially 1/8 of K, and well, I'll move that to the other side. So I have mg 30. I'll see if I can not plug in my numbers until the last step. Half mg. All right, and K is 8 times whatever that is. Okay, and I think I can also factor mg out. Okay, so 30 plus 1/2. Okay, good. So we'll plug, and this step is all algebra, and then the rest is what I call calculator work. So you can, when you study, try to distinguish the physics, which is usually the setup. So do you understand if you cannot set something up, it means you're weak on the physics. And then there's the algebra part, which is sort of plugging in and rearranging things before you do the final calculator part. Okay, and this is the part where we grade you have the least amount of points. So a lot of students put a lot of focus in plugging the right numbers in sort of these two steps, but in terms of grading scheme, we put the most emphasis here, second emphasis here, third emphasis here, right? So if you just screw up the answer, you might just lose 1 mark, 1 point if you get everything else above correct, okay? So roughly, if it is a 5-point scale, roughly think of it as 3 points, 1 point, 1 point, something like that, okay? 8, yeah, so M is 1, G, I'll use 10, here is 30.5, okay, good. And now you can plug in the number. Yeah, I'm not going to do that, but it's trivial. You get a number. what's the units? Okay, there's a couple of ways you can figure that out. You can either find the initial formula over here, right? K is 2 times energy of spring divided by delta X square, right? So if I rearrange for K, so what is the units? Well, 2 doesn't have any unit, so it's joules per meter squared. Okay, so you can put in whatever that number is and joules per meter squared. Okay. If you have used another formula, let's say F equals to minus Kx, we haven't talked about that. By the way, meters, this is change in distance, but change in distance is also, the position is measured in meters, so change in position is also meters. Yeah, we haven't talked about this formula, but if you do use it, then you will have, right, force over that, so it's newtons, the units, put in brackets, the units is newtons per meter. And you might think, hey, is that a contradiction? It's not a contradiction because joules and newtons are also composite units. It's not the base units. If you think about what is the base units, if you change everything back to SI base units, which means everything you learn in physics should be able to make up of, there's actually 7 of them, but these 3 are the most basic ones. In 3A, you always just use these 3. In 3B, you have a couple more, like coulombs or something like that. Actually, amperes is the base unit, but yeah, the SI units are made of 7 basic ones, but in 3A, these are only the 3 that will make up almost everything else. So what's newtons? So you can figure out by any formula like this, right? If that's newtons, so the units for F is newtons, the units for M is kilograms, the units for meters, acceleration is meters per second. So Newton is really 1, so if you think of 1 Newton times 1 kilogram times 1 meters per second square, so 1 Newtons is really identical to kilogram meter per second square, okay? And what is joules? Joules, let's pick something else, right? This has the units of joules, half mv square. So 1 joule is equals to half, doesn't have a unit, but m has kg, v square, right? So it's meter per second square, so meter per second and then squared. So 1 joules is kg meter square per second square. So what's K? So K is joules per meter square. So the spring constant has a unit of kilograms per second square. Okay. If I use this, what if I use this? Well, I need to take this and divide by meters, right? So K has the units of Newton, which is this, divided by meters. So I just have kilograms per second square. You see, it's exactly the same thing. So just because you use joules per meter square or Newton per meter, it doesn't make a difference. So both of them is completely acceptable. Spring constant is not something that important that we have its own name. We don't invent a special unit for spring constant. So actually Newton per meter is more common, but if you put joules per meter square or if you put kilograms per second square, anything is fine. Yeah, as long as it's correct.